I'm going to discuss some problems today for the second test. I already posted those sample tests online, and I hope you find the time to work out those problems. Okay, so let me just complete the 10 problems first. If you have questions, you can ask me. The test will be given on this Friday. Okay, the first problem I want to discuss is about how to find tangent line to a curve, but that curve is given by a parametric equations. Okay, so find the tangent line to the curve. Okay, the curve is given by the following two equations: x equals this, and y equals tq minus 2t at the point when t equals 2. Okay, now you really don't need to find this points, the xy coordinates of the point. All right, so there's a curve passing through some point, and you want to find the tangent, right? So if this is a curve, is a graph of some function, then the slope, right, is going to be dy over dx at that particular point. If this is a x naught, y naught, then x should be equal to x naught. Okay. Since then, you have to express y in terms of x. It's not easy to do that because you cannot solve for t in terms of x and plug into the second equation. By the chain rule, okay, this is going to be dy over dt over dx over dt. Okay, and this is going to be when t equals t naught. Okay, so this is also this is a general formula. Okay. Now our point right now is going to be 2, t equals 2, right? When t equals 2. So you have to find the derivative of y with respect to t and derivative of x with respect to t first. So let's find out the derivative. So 4t cubed minus 4t, okay? And the derivative of y with respect to t is going to be 3t squared minus 2. Okay, so the slope is going to be the derivative of y with respect to t. It's a 3t squared minus 2, 4t cubed minus 4t, and evaluate when t equals 2. Okay. All right, so let's do it. It's going to be 3t squared minus 2, 4, and 2 cubed minus 4 times 2. Okay, let's simplify it. It's not easy to simplify, actually. And 4 times 3, 12, 12 minus 2 is 10. Then here I have a 4 times 8 minus 2 is 6. Okay, so you can simplify a little bit. It's going to be, this is going to be 5. The next one divided by 2, 3. Okay, it's going to be 12. Okay, so that is a slope. Okay, you still have to find out x naught, right, and when, because this is a point, in the equation we're going to use the point, coordinates a point in the equation. So it's 2 to the 4th power minus 2 to the square and plus 1. And how do you do the computation quickly? This is a 2 to the 4th minus 2 cubed plus 1, right? Don't multiply this out. You just take 2 cubed out. It will be 2 minus 1 plus 1. Then you see that 2 minus 1 is going to be 1, and 8, it's going to be 9. Okay? So y naught is going to be 2 cubed minus 2 times 2. That's the same story here as 8 minus 4, it's 4. So now you get a point, you get slope. The equation will be, it will be standard. Okay. So let's call it point slope form. Okay. All right, so that's it for the first problem. The second one is still about equations, drawing, and polar equation. You're given polar equation, sketch the graph, and also in some problems you have to find the you have to find the area of the area of the region enclosed by this polar curve. So I equals 1 plus sine theta. Okay, I sketch the graph, and I add one more question. Find the area of the region, okay, enclosed by about the curve, by the polar curve. Okay, the polar curve is closed. Now, this polar curve, R could be 0, but R never be negative. Notice that, okay? Observe, that R equals 1 plus sine theta is greater than or equal to 1 minus 1, which is 0. It's never been, but somewhere it's 0. Okay, when the curve touches the origin, okay? So you have to make a chart, and this is a theta, and here's R. It's periodic function. When x equals, when theta is 0, I is 1. When theta equals pi over 2, that's sine pi over 2 is 1, that's 2. And this is going to be pi, it's going to be 1 again. And the 3 pi over 2, this is the time, it's going to be 0. Okay, it's 2 pi, it's going to be 1 again. Okay, so you get pretty good idea about the graph. And this is an x-axis and a y-axis. Okay, so here's a 1, that's a 2, that's a negative 1, that's a 0. So graph goes to these two. Okay. All right, so this is a completely closed curve. Okay. Now, there are only 3 types of circles, closed curves for this type of equation: a plus b sine theta or cosine theta. Okay, so this is things r equals 0 somewhere, so that's why there's a point on the curve touches the origin. All right, then you write down the area formula. It's going to be integral from 2 times r squared d theta, right? And write down this, and then you square it. What do you mean 1/2? This is the one divide. This is the formula. Yeah. Yeah. So 1/2 divided by 2. Yeah. This is a formula. Yeah. So, all right. So then you multiply this out. It's 1 plus 2 sine theta and plus sine square theta. Sine square theta. Remember, cosine 2 theta equals 2. So 1 minus sine 2 theta. Yeah. 1 minus 2 sine square theta. So sine square theta will be 1 minus cosine 2 theta divided by 2. Okay. And I really don't need to worry about integral of sine theta, integral of cosine 2 theta. So 1 plus 1/2 is going to be 3 over 2. Then I have a 2 pi. So after that, I'm going to get 3 pi over 2. So I skip some steps here. Just evaluate this integral. All right. So for polar curves, so for the rest of them, they're about series and the power series, Taylor series. Okay. Not everybody fully understand this material. I can see that from the quizzes. Okay. What do you mean differentiate part? You mean the integral? Yeah, I skip it. I just give it the answer here. I don't want to waste too much time on evaluating this integral. Okay. So just square it and you know how to evaluate the integral. All right. So the next one is this is the function 1 over x plus 1, and find the power series representation for f of x at a equals 1. Okay. Now, if you can find this one, you can also answer the question: what is the Taylor series of this function? Okay. Now, what we needed to know is we have to recall the formula, and this 1 minus 1, 1 over 1 minus x is going to be there's no denominator, just x to the power n, and this holds for x absolute x less than 1. Okay. I needed this fact. You can write down this formula first before we solve the problem. Okay. So, but I have 1 plus x, but I actually need I want to get power series at a equals 1. So x equals x minus 1. This is the part I like. Okay. X minus 1. Okay. So this, for simplicity, I'm going to use, let's u here plus 1, and u is going to be x minus 1. I'm going to expand it in terms of u. Okay, not x. Because if I can express the function as a power series of u in u, then I get the power series representation for the function at a equals 1. So f of x is going to be x plus 1. What is x plus x? X is u plus 1 plus 1. Okay. So now I get 2 plus u, right? But this does not look like the one I have here. 1 over 1 minus x. So I have to divide by 2. Then I get 1 plus u over 2. Very close. And x is going to be, if you use the above formula, this is going to be 1 minus negative u over 2, okay? So now, using the above formula, it's going to be, that x is going to be negative u over 2. So negative u over 2 to the power n. Okay, then you simplify it. Negative 1 to the power n, divided by 2 to the n, but I have another 2 coming from the front. That's 2 plus 1, and the u to the n. Okay. Then I replace u by x minus 1. Okay, and this holds when u is less than, absolute u is less than 1, i.e., because u is is when half of u less than 1. So that means x minus 1 is less than 2. Right, the same. So you get radius of convergence, which is 2, and you get a power series representation for that function, okay, around the 1. So you have to use the well-known result. This is a table 1 on page 808. Okay, memorize all the power series on the table 1. Yeah, table 1 on page 808. Okay, we have to know this, all the formulas in that page. Right. The next one is to determine the series, whether the series is convergent or divergent. And you have to prove your claim, okay? Now, what happens if the answer is correct, but your reasoning, your argument is wrong, okay? And it's harder for me to give you credits, okay? Because I give points to the solution, not to the answer. Okay, remember, solution consists of the argument and the answer. Okay, when I say determine whether the series is convergent or divergent and prove your claim. Okay, you cannot just by guessing try. Okay, oh, convergent, that's it. Okay, or given nothing, just convergent. Okay, then you maybe only get 20% of credit. Okay, but if you give a wrong argument, that's okay. You know, I don't give extra credit. Even you write lots of stuff there. It's irrelevant. Okay, so you have to find right argument to that. You know, if you look at this 3 plus sine u, right? Sine n. This is a sine n changes, but it changes the values in some way we don't know, right? But anyway, sine u, sine n is between -1 and +1. That's what we know, right? So then that implies 3 plus sine n is greater than equals 3 minus 1, which is 2. Okay, but it's also this is also less than equal to 3 plus 1, which is 4. So there are some number in the denominator. It's between 2 and 4. Therefore, it's less than equal to 1/2, greater than 1/4. Okay. So the nth term is always between those two positive numbers. It does not apply. It does not approach 0. Okay. So this implies this nth term. I don't care whether the limit exists or not, but this is not going to be 0. That's clear. Maybe that. I think this doesn't exist, but we're not going to prove it. Okay. All right. So what does that mean? That means the series is divergent. Right? The series is divergent by the test for divergence. Now, what is the test for divergence? The test for divergence says that if this series is convergent, then the limit of the nth term is 0. Okay, that's called a test for divergence. So now you have a series. Limit of n is not going to be 0. Of course, then it's divergent, right? Because if it's convergent, then the limit of n is 0. But these two are not equivalent. The limit of n equals 0 does not mean the series is convergent. Conversely, it's not true. This is just a necessary condition. Okay, and look at this. Okay, this is divergent. Okay, and the limit of the nth term is 0. Right. So the limit of n 0 does not guarantee the series is convergent. Okay, but if the series is convergent, the limit of nth term must be 0. Okay, so if you try to prove something convergent, just look at the nth term. You know, the limit is equal to 0. Then you say it's convergent. No, the sequence is convergent, but the series is divergent. Sometimes you cannot guarantee the series is convergent. There's a difference between series and sequence. The series is just the sum of this infinite many terms. The sequence of the nth term is just those are the numbers, right? Sequence of numbers. All right, is there any other method you can prove that? Well, you can prove that using comparison test. Because actually what I'm doing is kind of a comparison test, because I prove that the nth term is greater than 1 over 4, right? It's actually it's a comparison test. N equals 3 plus sine n. It's greater than equal to 3 minus 1, 3 plus 1, which is 1/4. That's my Bn, right? Yeah. You don't need to use test for divergence. Okay. Then what? Sigma of this Bn, which is a quarter. This is going to be infinity divergent, right? It's divergent because every term is 1/4. And, infinite many terms, 1/4. Of course, it's divergent. It's constant, right? This implies is divergent by the comparison test, right? So you can view that's a second method, but it's much simpler, right? Yeah. Okay. Yeah. If there's no technical issue, I will post it. Okay, sometimes not 100% guarantee. Okay. Did you get my YouTube video? Yeah. Okay, that's the first time I tried. Okay. Okay. Yeah. So I'm going to teach 261 multivariable calculus. So if anyone who wants to take it, register that. Okay. 261 is multivariable calculus next semester. Yeah. All right. So so this is what I have. Yeah. Now we want to determine whether this is a convergent or divergent and prove your claim. The same argument, right? When you look at that, okay, it's alternating series. Now my suggestion is you still have alternative ways to do the problem. Don't just look at it's alternative series and begin with the alternative series test. Maybe that takes much more time because you have to prove it's decreasing. Okay. Now, if we can prove it is absolute convergent, then it's convergent, even more than we need, right? Okay. So determine whether this series is convergent or divergent and prove your claim. But if you are able to prove this is absolute convergent, then I think it's convergent. Okay. So what I'm going to do is instead I'm not going to use it, consider as alternating series. I'm going to use a ratio test and rotor test to prove it's absolute convergent. Okay. So this is my n. It involves signs. Okay. So what I'm going to do is I look at n plus 1. The reason I use a ratio test is it's exponential function, 2 to the n. Okay. So this is going to be, the sign is already gone. It's n plus 1 squared, 2 to the n plus 1, n squared over 2 to the n. Okay. Right, so let's simplify it, right? N plus 1. Okay. After simplifying, I get this. Okay. Then I continue to simplify. I get 1 plus 1 over n squared and 2/2. Okay. And then clearly the limit is going to be 1 times 1/2 as n goes to infinity. So if the limit is less than 1, it is absolute convergent. Okay. So clearly this is a less than 1. Then this series okay, is going to be is absolutely convergent, okay, by the ratio test. Okay, by the ratio test. Okay, therefore it is convergent. You know, if we just ask for whether it's if we ask it to check whether it's convergent or divergent, then you still have to say that. Therefore, it is convergent. Okay, it's supposed to converge. Of course, it's convergent. Okay, you don't need to mention the theorem because there's I think called theorem number 5. There's no special name for that. Then in that case, you don't need to mention that. You can say by the theorem in the book. Okay, that's okay. It's just all right. So you can similarly prove that using rote test. Okay. Okay. We can prove it using the rote test. Yeah, we can also prove it using rote test. Okay. Now, that's the first method, right? And if you really want to use an alternating series test, that's okay. It's guaranteed. It's continued. So using alternate series test, right? This is let's go back to the problem. Okay, this is n squared over 2 to the n. That is my Bn, right? Yeah. So we are going to view it as a series like that. It's alternating series. So I needed to look at Bn. Bn, of course, is positive, right? So Bn is positive. And Bn decreasing, I have to prove that. The third one is Bn approaches 0, right? The two statements. I think neither of them, you have to prove 2 and 3. Okay. Just look at the function f of x, and look at the x squared over 2 to the x. I have to prove it's decreasing. How to prove it? Find the derivative. Should be negative. Right? And to prove the limit is 0, you needed to use L'Hopital's rule, for example, right? So let's look at the derivative of the function. It's 2 to the x squared, and that will be 2x and 2 to the x. Then minus x squared, the derivative 2 to the x will be 2 to the x natural log of 2. So I take 2 to the x out. I also take x out. Then I get 2 left here. Then I get 1x left. Then I get natural 2 left, right? Yeah, that's 2 to the x squared. Now, this is going to be negative if x is greater than 2 over natural log of 2. I don't know how big of that number. You can do rough estimate, but if you don't have a calculator, forget it. This is just a positive number. Maybe 5, then maybe 6, close to that. That's okay. This is a number. It's a positive number. Okay, some number larger than 1, clearly. Okay, but I can do the estimate. Natural log of 2. Yeah. Yeah, it's okay. We don't need to do that. All right, so that means f of x is decreasing on the interval from 2 to on this interval. That's good. Okay, this implies Bn decreasing for some larger n. Okay, we don't need to know what is n, okay? But I also want to take the limit. Look at the limit, yeah. So the limit, it's infinite over infinite type, so you can use the L'Hopital's rule all right? Both goes to infinity. So you can use a L'Hopital's rule to this. So it's 2x, 2 to the x natural log 2. But still, I have to continue. It'll be 2, and then 2 to the x, natural log 2 square, and clearly it's going to be 0. All right, so this implies that Bn is going to be 0, the limit of Bn. You see, so complicated if you use the alternating series test. Okay, so therefore, is convergent by the alternating series test. So remember, it will be misleading. When you see this -1 to the power n, don't just always jump to the alternating series test. And you can do it, but it takes much more time. Another alternative series right now. Okay, let's take a look. You see, here's another one. You cannot actually, this particular problem, you cannot use alternating series test to prove it's convergent. As a matter of fact, this is divergent. Alternating series test can be only used to prove alternating series convergent, if it is convergent, okay? If it's divergent, alternating series test is useless. You cannot say one of the conditions is not satisfying in the alternate series, therefore it's divergent. It does not say that, okay? The statement says that if the 3 conditions meet, right, are satisfied, then the alternating series test, by alternating series test, this series is convergent. That's it. You cannot use that to prove divergent. But when you look at this series, it's obvious it's divergent. Can you see that? Why it's obvious? Obvious. At the moment when you look at the series, it's divergent. You can see that. No, the limit is not going to be negative. Has no limit. Has no limit. So this is the n. N has no limit. Okay, of course, the limit is not going to be 0 because the limit doesn't exist at all, right? Okay, so the limit of n squared minus 1 over n squared plus 1 is going to be 1. That's obvious. But the limit of n does not exist because it's jump always from between, almost negative and almost positive. It does not approach to any fixed number. Okay, so therefore, okay, it is divergent by the test for divergence. That's it. There's no other method you can use for this particular problem. If you use a ratio test, you cannot prove it's divergent. If you use a root test, it's impossible. What is the nth root of that? Okay. If you use, we never use a ratio test for term with polynomials, numerator denominator. Only when you see n factorial and you see a to the power n, you can consider the ratio test because the limit. Okay, look at that. You cannot use a So I guarantee the limit of n plus 1 over n is going to be 1. Inconclusive using the ratio test. Okay. Okay, there's some students come to my office to make up a quiz. Okay, in trying to find the limit of this, the limit Okay, I hope he can find the limit. Okay, the limit actually is 1, but of course he can find different limit. Then jump to the conclusion is convergent, or it's divergent, But that's the argument. Suppose you jump to the conclusion it's divergent. How many credits I give to you? Okay, you are based on wrong argument to get to divergent, but the answer is divergent, right? Okay, so answer is divergent. Honestly, I can give you 50% of the credits if you just put say divergent. Nothing is there beside that. Okay, as long as I don't suspect you copy from student sitting next to you, then I say at least you have some insights. You see this divergent. They don't know how to put the argument. But if you use a wrong argument, right, leads to, because there's only possible answers, divergent, convergent, right? The 50% chance you get the convergence, right? But if the answer is correct, it's hard for me to give you credits because that you did not even see this is a divergent at the very beginning, and you use a wrong argument, it's useless argument. But because you jump to that conclusion because you did a computation mistakes, okay. Now you should see it's divergent. Yes. No, it's not necessary. I just say that if you use a ratio test to be inconclusive, you don't need to put the extra stuff there. Okay, maybe on your scratch paper, you find out inconclusive, but don't need to put that information there. You're going to prove it's divergent. Okay. Yes.
This test, the test for divergence, is sometimes called the end-term test.
Yeah, that's okay. Oh. Now, if I ask you to use the integral test, you have to use the integral test. Okay, so here's a series, n(e) to the n squared. If you use a ratio test, why you can use a ratio? If you use a ratio test or use a root test, you can prove that it is convergent. Okay, I guarantee it. Okay. But I want to use the integral test. Okay. So the integral test, this is my n. So n equals f of n. The function f of x is going to be x e to the negative x squared. What I have to do, remember the ratio, integral test, I have to say the function is positive and decreasing, right? I have to prove it's decreasing. Okay. So the derivative of this function is 1 e to the negative x plus x e to the negative x, then times the derivative of negative x squared. Okay, so I get e to the negative x, 1 minus 2x squared. And I think this is going to be negative for x greater than or equal 1. Right? It's greater than or equal 1. So it's decreasing on the interval from 1 to infinity. Therefore, I can use the integral test. Okay? We can use, otherwise you cannot use the integral test here. Okay, so then you consider this integral from 1 to infinity f of x dx. Then you have to use a substitution to solve the problem. So use a substitution, you let u to be x squared. Then du equals 2x dx. And this integral still be 1 to infinity And just because u, and when x runs from 1 to infinity, u runs from 1 to infinity. And that's this e to the negative u. And I think it's half of du. Okay? So the antiderivative is this. And evaluate at the end, two endpoints. I think the answer will be half of e to the negative 1. All right, you can think about it, okay? So when u approaches infinity, then e to the negative u approaches 0. Okay, so this is a finite. It's convergent. So therefore, you can get this is convergent, okay, by the integral test. All right. We can use as a test to prove it's convergent. Now, let me try it. Okay. We can also use as a method, okay, if it's not specified, okay, to show the convergence. Okay. For example, I look at its power function, more than power function, exponential function, e to the negative. So I use a ratio test. Okay. So the ratio test is a little bit complicated. It's anyway, it's positive. So it's going to be n plus 1 e to the negative n plus 1 square and e to the negative n square. The question is, how do you simplify? This is a place. I remember I put it, this problem, similar problem on the makeup quiz, and there was a student that couldn't find the limit. Okay, but still get the same conclusion. Hey, it's convergent, but that's incorrect argument. And how do you simplify? Right? How do you simplify? Well, the first term n plus 1, right? This is clearly going to approach 1. And then that's going to go to the denominator, actually. Right? Clear, right? Yeah. The negative sign goes to the denominator. So after you simplify, and n plus 1 square is n square plus 2n plus 1. So it's 2n plus 1. That's what is left. And clearly, it's going to be, the limit is going to be 0. Why? Because the denominator is getting large and large, right? So the limit is 0. So the limit is 0 means it's less than 1, right? Okay. So then this implies this, because it's positive, all the terms are positive, is convergent by the ratio test. Right? So you can use as a test to prove it's convergent. Now, if I ask you the integral test to prove it's convergent, and we use a different test to prove convergence, sometimes depends. Okay, if I'm not very happy at that moment, I give you 50% of credits. Otherwise, this is it's irrelevant to your argument, to do the, because I ask you the specific method. I'm testing you whether you know this method. Now you give me, right? You give me different argument. Okay. So let's use a rote test. It works too. Okay. Okay. So this is going to be n root n e to the n squared, right? Right. So that's going to be e to the negative n squared over n, just n. And clearly, this approaches 1 times 0 and approaches infinity. Okay? It's still less than 1. So that implies is convergent by the rote test. Right? Any other test you can use to prove it is convergent? Well, other methods a little bit more complicated, such as like a comparison test. Okay, you have to find genius, you have to find a BN. So I don't recommend, with trying that. Yeah, because AN should be less than or equal to some simple term, BN. And how do you find it, right? All right, so let's do next problem. Now this time we have to determine whether this is a absolute convergent or condition convergent. Okay, so let me write down the whole question. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. I prove your statement. So here's a series. And at the moment when I see it, I think it's absolutely convergent. Why? If you remove the negative sign, this is going to be P series, 1 over n squared. It's convergent. So it's absolute convergent. Okay, how do you do that? You look at, this is your n, okay? You look at the absolute value of this, which is just n squared plus 1. Right? This is less than n squared, which is a Bn. And clearly it's P series, right? So I know that this is a convergent by the P series test. Okay, P equals 2 greater than 1. Okay, so by the P series test, what you can say at this moment, you can only say the absolute value of this. This is a convergent, okay, by the comparison test. Yeah, you take absolute value A, then you will get a series with positive terms. Then you can use a comparison test. So you estimate it, you get upper bound and the simplified upper bound Bn, and then you find out sigma Bn is convergent. Okay, then by the comparison test, sigma of absolute value is convergent. Okay, that's by the comparison test. Then by the theorem in the book, this is a this is convergent, but I think absolute, just absolute convergent, you can say that. Okay. So this is absolute convergent. Okay, by definition. Yeah. Absolute convergent means if you take an absolute value of each term, it is still convergent. Okay, we are given the power series. We are going to find the radius of convergence. And, okay, here's another question. Interval of convergence. Okay. And this power series is going to be like this. Okay. I can tell you immediately the answer at the moment when I see it. It's interval from -1 to +1, including -1 and +1. Okay. The reason is the radius of convergence is going to be 1. It's obvious. Why it's obvious? Okay, you know, when I know sigma xa, if you modify or change the coefficient to any polynomial type coefficient, like n squared, you don't change the radius convergence. And the secant of n squared is a denominator, so it is convergent at the two endpoints, at negative and positive. So what I'm going to do is, I'm not going to, no, I'm going to use a ratio, root test, okay? A ratio test, doesn't matter. So this is n. Absolute value of this is going to be n plus 1 squared. Okay, so after simplified, I get n plus 1 squared, n squared. Then I have this. So the limit is just absolute x. Right. As n approaches infinity. So by the ratio test, what do we know? The absolute of x is less than 1, it's absolute convergent. Okay. So by the ratio test, we see that by the ratio, I don't need to put absolute value here. I just say this is absolute convergent if this is less than 1. This is a divergent if this is greater than 1. All right. So the radius convergence clear, just 1, right from here. I is going to be 1. But I want to know the interval convergence. I have to look at the endpoints. The endpoint, okay, how actually can do together, okay? At the endpoint, okay, absolute x is going to be 1, right? Yeah. I don't need to look at the both sides. I just doesn't matter, combine them into one argument. So this series, okay, I consider whether it's absolute convergent or not. Okay, this is going to be n squared, right? But absolute x is already 1. So this is going to be n squared. This is a convergent because it's p series. Okay, so that means at the two endpoints, not only convergent, it's absolute convergent. Okay, so this series is also absolute convergent at the endpoints. Is absolute convergent at x plus minus 1. Okay, it's that. Then you get an interval convergence. The interval convergence from -1 to +1. All right. Our next question is how to find Taylor series for a sequence. For a function here. Find the Taylor series for the function f of x at a equals 1. All right, there are two different ways to find the Taylor series. I said that. One is by the definition, method one. By definition. Right? By definition, the Taylor series is going to be this. Okay, so you have to find all the derivatives and evaluate the one because it's polynomials. They're not that difficult to find the derivatives. Okay, so what I'm going to do is, yeah, you get f1, sorry, plus f prime 1, 1, and x minus 1, and plus f double prime 1, 2 factorial, and f triple prime. And that's it. You're not going to get a higher order derivative. The rest of them would be 0, a higher order. Yeah, that's right. By definition, you have to find the derivatives. Because what is Taylor series? By definition, is series like that. Coefficients are determined by how the derivative of the function. So you have to find all the derivatives, right? So you have f prime x equals 3x squared minus 6x plus 3. F double prime is 6x minus 6. F triple prime is going to be 6. Then higher order derivatives will always be 0. Okay. That, right? Then you evaluate at the 1, the 1 minus 3, negative 2, it's going to be 1. Yeah. Then I look at f prime 1, it's 3 minus, it's going to be 0. Yeah. Then f double prime, it's going to be 0. F triple prime is going to be already 6. So my answer will be, I don't need to say x equals that. So this is going to be, the first term is 1, the second term is 0, the third term is going to be 6 over 3 factorial x minus 1 cube. Okay, it's going to be 1 plus x minus 1 cube. That's it. The rest of them are 0. Yeah, I put the details, So I get, you get the it's going to be F1, right? So, so it's 1 plus 0 over 1 factorial x minus 1, 0 over 2 factorial x minus 1 squared, and that's going to be 6 over 3 factorial x minus 1 cubed. And the rest of them are 0 plus 0. Okay, after simplifying, it is just those two terms. So this is the Taylor series for the function at 1. The second method is to express, to find the power series for the function. Okay, finding the power series representation for the function, okay, at a equals 1. But this function is going to be polynomial. So there's a quick way to do. I'm going to look at, okay, there's a quick way to do. So actually, this is x cubed plus minus 3x squared plus 3x, right? So this is actually is going to be, and that part is going to be x minus 1 cubed plus 1. So I can quickly get that. Otherwise, you have to let x to be u plus 1, u is x minus 1, you can Okay, that's a quick way to do. You can also use the next method. X is going to be x minus 1 plus 1, which is u plus 1. Okay, so and then f of x, power series representation for the function. And then power series is going to be the Taylor series by the theorem. Okay, so that means it's going to be u minus 1 q minus 3u plus 1 square plus 3u plus 1. And after you expand it, I guarantee this is going to be u cubed plus 1. Okay, after you simplify, which is going to be 1 plus x minus 1 cubed. So this is the power series representation for the function at work. And this is just polynomials. This could be 1 of x, could be natural log of x. Okay, all kind of, okay. So you have to use the well-known power series representation for those functions to get a power series representation for this particular function at 1. Then you can solve the problem. Okay.